Hello, in this video I'll be showing you how to find the equation of a plane given 3 points. So we'll just start off by looking at an example here. Determine the equation of a plane given the points 1, 0, 0, 0, 2, 2, and -1, 0, 3. So the way we do, so basically a plane, it looks something like this. It's a three-dimensional, it goes on forever. This is a x, y, and z axis. X, Y, Z, as some arbitrary, it's like imagine a piece of paper and you can have it like facing downward on an XY plane, or you can have it kind of like this on a plane. It's basically just a surface that goes on forever in a three-dimensional space. So the way we actually define a plane, unlike an equation, we have to define a plane in terms of a normal vector, because we can't choose any point on the plane to define it, because there's like an infinite amount of points here. So the way we define a plane is R dotted with N equals A dotted with N. So N is our normal vector and A is any and every point on the plane. So A could be here, it could be there or there, and R is the vector x, y, z. Okay, so that's some of the terminology. So that's how we define a plane. It is the dot product of the R vector dotted with the normal vector, and it's equal to any point and every point dotted with the normal vector. So the way, with our 3 points here, let's just draw them out. So I'm going to label this point A, this point B, and this point C. So to find a normal vector, we have to understand what we're actually looking at here. So we have the points A, B, and C on some plane. Now, to define a plane, we need to find our normal vector. The way we find our normal vector is we've got to find a vector that's, so to find the normal vector, we need a vector that's perpendicular to a plane. So the way we do that is we find the vector AB, AC, and we find the cross product of these two vectors here. Because recall, if you find the cross product of two vectors, it gives you a vector perpendicular to the two vectors, which would be the normal vector, because the points A, B, and C are in the plane. You could also, you don't have to do it from A to B, you could do it from C to B, or you could do it from B to something, to A. You can do it pretty much any way, as long as you choose one point as your basically your center point, and you point the arrows in this direction. Oh, whoops. And you point the arrows away from it. It will not work if you, so basically just choose, so simply choose it so it looks something like this, and you'll always get the right answer. So now that we understand what we're looking for, so we need to find a normal vector, and the way we do that is we find the vector AB and the vector AC, and we cross them together. So I'm just going to write that up here. So we have the vector A to B cross with A to C will give us our normal vector. Now we've got that terminology, I'm going to get rid of this diagram and we're going to find our vectors. So let's just say, so this is the point O to A, this is the point O to B, and this is the point O to C. Whoops. So A to B is equal to negative O to A plus O to B. Because if we had A here, B here, and the origin here, to find this vector here, which is A to B, you would need to go backwards from A to O, and then from O to B. So you need negative O to A plus O to B. So that's a geometric representation of this stuff here. Right, so we can write out our points in vector notation. So we'll go A to B is equal to negative 1, 0, 0 plus 0, 2, 2. Working that out, we get negative 1, 2, 2 as our vector A to B. I'm just going to move that up there for now. So that's our vector A to B. Similarly, we've got to find A to C now, because we're looking for a diagram like this. So we have, this is A, B, C. That's what we're looking for. So, oh, whoops. A to C, negative O to A, plus O to C. So that's equal to negative 1, 0, 0, plus negative 1, 0, 3. And that is equal to negative 2, 0, 3. Right, now that we've got both our vectors, we need to cross them. So when you cross two vectors, you basically put it in a 3 by 3 matrix, and then you find the determinant of each of the parts. So A, B crossed with AC, you put it in a 3 by 3 matrix with the vector components on the top row up here. So you have I, J, K. Then you're going to put this vector in this row here. So you're going to put negative 1, 2, 2, and then you're going to put this vector down here. So you're going to have negative 2, 0, 3. And that's our 3 by 3 matrix. Now, now you've got to break this up. So to find the x component, you need to find the determinant of this 2 by 2 matrix. So we rewrite it like 2, 2, 0, 3, I. Then you're going to have to put a minus here. So I'm just going to move our diagram, because that's going to get in the way up here. It might be covering the question, but who cares? Once that's for the x component. For the j component, you need to find the determinant of this 2 by 2 matrix. Ignore these numbers here. Just look at the matrix negative 1, 2, negative 2, 3, j. And for the k value, find the determinant of this, the determinant of this 2 by 2 matrix here. Plus negative 1, 2, negative 2, 0, k. Now you might have noticed, why did I put a negative here? So when you're finding the cross product, you need to have this order, whether it's with the 2 by 2. When you find the cross product of a vector only in 2 dimensions, you don't really have to you do have to always have this minus here. You got to go plus, minus, plus, minus. So if we had a 4th vector component, we would have another minus in front of the next matrix. So you got to always have plus, minus, plus. Right. So recall when you have a matrix A, B, C, D, and let's say this is matrix A, the determinant of A is equal to AD minus BC. So that's just a little side topic, this stuff here. So I'm just going to delete that now. So that's how we define the determinant of a matrix. So I'm just going to rub out this huge 3 by 3 now, and I'm going to move these other matrices across, because we know what we're already finding. We find the cross product. So I'm just going to move all this here up here. Right, so with this matrix here, oh, that's a really bad 2. This matrix here, to define the determinant, you need to multiply these two, so 2 times 3 minus the multiple of 2 times 0. So that's going to be equal to 6, therefore it is 6i. That's our x component. So I'm just going to get rid of that now. And I'm going to move this up here. And now we've got this matrix here, so we have a negative, negative 1, 2, negative 3. Oh, that's not negative 3. 2, 2, 3. So we need to multiply these two. Remember, we're going to have a negative outside the entire thing because we have this negative here. So it's negative 1 times 3 minus 2 times negative 2. And there's a whole bracket around that. So that's going to simplify to, there's a negative, so that's going to be negative 3 plus 4, which therefore is negative j. Whoops, I moved it down a bit. Negative j. So we're just going to rub all this out now. And move this up. Whoops, that is very yucky. Alright, and our last matrix, negative 1, 2, negative 2, 0. So it's going to be negative 1 times 0 minus 2 times negative 2. So we're going to have 0 plus 4k. So plus 4k. Now, what have we found? So we said earlier at the start of the video that we defined a plane as basically just a normal vector and n dotted with n. That's how we define a plane. What we found is the cross. We've basically found the vector that's perpendicular to. We basically found this vector here. So this is that vector here. So we've found our normal vector. So our normal vector is equal to 6, negative 1, 4. That's the hard part of basically finding the equation of a plane, doing the cross product, because a lot of people forget the minus sign here. And of course finding the determinant. Right, we've got our normal vector now. So what do we do now? Well, we gotta look at this formula here. R dotted with n equals an. So A is point on the plane. A is any point. So we can choose either A, B, or C because they are points on the plane. And no matter if you choose A, B, or C, you will get the same answer dotted with the normal vector. And just to show that, I'm going to do A and then B and then I'm going to do C. So we're just going to, we'll use A for the start, so we'll go A dotted with our normal vector. Recall when you dot something, you multiply the components and you plus them together, so you get 6 times 1 plus 0 times negative 1 plus 4, well, I'm just going to move that A, 4 times 0. So we get 6. Right. Now let's check if we get the same answer with the other points. So we'll get the point B, we'll go 0, 2, 2, dotted with our normal vector, 6, negative 1, 4, 6 times 0, plus negative 2, because that's actually 2 times negative 1, plus 4 times 2, simplifies to 6. And we'll check with our last point as well. Let's go C, negative 1, 0, 3, dotted with 6, negative 1, 4, 6 times negative 1, plus 0 times negative 1, plus 3 times 4. So you get negative 6, 12, plus those together, you also get 6. So it works for any of the points up here. It works for A, B, or C because they are points on the plane. Does that make sense? So if you found the normal vector and the question asks, determine whether, and they gave you some random, let's say they gave you a point D, like blah blah, like blah, or something. They'd say, determine if this point is on the plane. And if you didn't get the same value that you've gotten for these other points, then that point obviously isn't on the plane. I hope that makes a bit of sense. So now that we've got a normal vector, we're basically just going to find our equation of a plane. So recall that R is the vector x, y, z. We know that this value is equal to 6. So we'll just go x, y, z dotted with 6, negative 1, 4 equals 6. Therefore you get 6x minus y plus 4z equals 6. And that is the equation of our plane given the points A, B, and C. I hope you found this video helpful. If you want a follow-up video either on the cross product or the definition of planes pretty much, please shout it in the comments. Thank you so much for watching.